And at this point, what I thought I'd do is introduce the topic of the panel, and that's looking at all the unexpected complications to our very large systems, and very often these large systems that are connected to other large systems in environments that we don't anticipate fully. And it brings up a lot of issues that may go undetected even when you're doing your own job really well. So today we have a couple of folks from the International Council on Systems Engineering, Mark Walker and Michael deLamare, who will talk a little bit about the role of that council and that group of engineers. And when they explain it, you'll see why that's a significant opportunity for us to bring national level, actually world-class level talent to this issue. Tom Popik is here for the Foundation for Resilient Societies, and he is an MIT engineer himself, but he's been very active in looking at the organizational complexity between organizations like NERC and FERC and state organizations who are trying to put their hands around all of this. And then Joe Weiss is interesting because he's been looking at this as an engineer, looking at a lot of the issues regarding cyber threats that are sort of obscure to most of us, and he'll give us 2 or 3 of the reasons why that is and how that sneaks up on us in unexpected ways in complex systems as well. So what I'm going to do is start by maybe having Tom Popik discuss from his point of view. And by the way, we'll have a few minutes for each of the panelists. Then they may have some opportunities for questions. But this is a very brief panel, so everyone's going to keep it to about 2 or 3 minutes now. You might hear from some of these folks later as well, and we'll have opportunities in between some sessions and lunch and so on to grab them for some more information. But we just need a general orientation. And Tom, maybe you can start us off.
Well, certainly. Thank you, Chuck. I'm going to be talking about the nexus of engineering and organizational issues, but I'd like to expand it a little bit more to also the political, economic, legal, and scientific arenas. So the first point I'd like to make is that reliable infrastructure is essential to human populations. We can all agree on that. But I'd also like to make a second very important point, which is countries and societies under stress have trouble prioritizing infrastructure reliability in advance of catastrophic events. And so we see this not only in the United States, but actually in other countries in the world right now. So for example, if we look at South Africa is currently having rolling blackouts because their society is literally having trouble keeping the lights on. If we go to another society, the United Kingdom, the reserve capacity margin for electric generation in the United Kingdom this winter will be approximately 1%. In November, the United Kingdom had to enact what's called demand response. They asked major consumers of electricity to shut down, such as factories, so they wouldn't have to have rolling blackouts. And then I'll even give an example here closer to home. In the winter of 2014, January 2014, we had the polar vortex, very cold weather snap. PJM came with, I should say with PJM, it's the largest reliability coordinator and transmission operator here in the United States. They cover from the Midwest all the way to here, the Washington, D.C. area. So in January of 2014, they came within 2 gigawatts of having rolling blackouts, and that's about 2% reserve margin. That's some of the societal stress that we're under. And then let's look at how we have reliability regulations set here in the United States. It's set through a public-private partnership with the North American Electric Reliability Corporation, setting standards through representatives of the electric utility industry, and then a federal regulatory body, the Federal Energy Regulatory Commission, approving these standards. And there's a lot of friction, dispute in the standard setting process. This is really a symptom of the overall societal stress and how we have trouble coming to grips with some of these very, very large issues of how we prioritize infrastructure reliability and protection.
Okay. Thank you, Tom. That's a good first overview. From another systems perspective, perhaps Mark and Michael will, and it doesn't matter to me which may go first, just give us a little overview of INCOSE and why these complex issues or systems are of interest to you in light of these very high-impact threats. And you might just mention a little bit about your interest, how you got interested in it, and what your roles are in INCOSE and so on, so people can get an idea of who you are and what you're about to do.
Yeah, okay, thank you. Chuck, Mark here won the coin toss, so I go first. I get the kickoff here. So let me just start by introducing INCOSE. What is INCOSE? You might not have heard of that before. It is an acronym standing for the International Council on Systems Engineering. It is the premier professional society of systems engineers. It's a 25-year-old organization with about 10,000 members in 62 countries. And it is a certifying body for SE professionals. It has about 100 companies on the corporate advisory board and in the government and with university representation as well. And it exists to push the state of the art in the topic of systems engineering. Applying systems engineering, if you're not familiar with it, is a discipline that was established primarily in space and defense and has been pushed out into other domains such as healthcare, automotive, industrial facilities, where I spend a lot of my time right now. As far as the interest in this, I am on the corporate advisory board for INCOSE. I also co-chair the infrastructure working group. And it was about January, Mark and Chuck were conspiring together to bring INCOSE into this because of the abilities that INCOSE has, the intellectual properties and the skill set that the members have in being able to model complex systems, for example. So we established in June of this year the Critical Infrastructure Protection and Recovery Working Group, which is in parallel in our charter to what the EMP SIG is doing. So we are working on supporting the activity of how do we protect our critical infrastructure, how do we recover from these events, and the way that the INCOSE is doing this as a professional society of all volunteers is by bringing in a systems approach to things and making that kind of skill set available to people in InfraGard and in the related organizations, trying to build partnerships with universities, with InfraGard, with public and private sector, with other professional societies such as the IEEE or the International Society of Automation, or EIA, which Electronic Industry Association, who are ISO, who are bodies that create standards that we would be able to influence and try to work this all together, from not just bringing in system principles to systems themselves, but to the more complex system of policy and human systems in that regard. So that's part of the way that we can provide expert assistance in dealing with complex systems, system of systems, model-based support, which I think Mark will address a little bit more about. System reliability, system resilience, principles and architectures, standards development, life cycle approaches, information distribution, and areas along that side. So with that, let me allow Mark to take this further.
Okay, as Mike has mentioned, INCOSE's really main objective is to establish a well-defined and formulated high-level system engineering in all different areas of system engineering and engineering and development of systems. So I've been, there's like 46 different working groups in INCOSE. A lot of them are process-oriented, like requirements, architecture, system of systems, complex systems. These are working groups. In addition to applying it, and that's where we're getting a little more into that area. I've been in INCOSE for 23 years or so. And so the separate working group is kind of okay, now let's figure out how we can really apply the high-level thinking of system engineering to a real problem. And obviously, all engineers are interested in challenging problems and how you solve them. So when you get into the EMP, the solar as well as the cyber world of the problems, you start thinking heavily on the negative sides of developing systems is how do you address those problems. So from a system point of view, we use the term system thinking. It's really trying to understand the holistic perspective of the problem and understand what the customers, and they can be good or bad. If you have obviously users you don't want using your system, that directly applies to failure modes, effects analysis, stuff like that, which is very valuable to determine how you design and develop the system from a complete point of view. It can also be multiple layers. Quickly thinking of this, I look at this problem as a 5 to 6 level of a system of systems point of view of how we're going to manage it from the many organizations that are involved that are very high level, and all the engineering you've got to do to connect systems at very high levels, as well as you go down into all the way down to the components that have to be fixed to protect them from being hit or something like that. So anyhow, model-based system engineering is a new concept we're implementing over the last 10, 15 years. It's based on models, but maybe not the dynamic modeling necessarily. It's more of anyhow, so I can't probably go too much more than this. But anyhow, it's key requirements. I just want to throw out one requirement. I mentioned this yesterday. There's one requirement that really applies to the problem we're looking at here, and it's called operational availability. I had to design a system one time that was a very high operational availability requirement. It's a combination of the design of the system for all failure modes as well as what you want it to do, in addition to the life cycle support aspects of it. If you have failures, how do you address them? So it's a one requirement that is extremely applicable to this problem that we really need to look at. We worry about all users, good and bad. You got to really look through that. Enabling capabilities, databases, all the information you want to save and pass, and how you do that. Obviously, cryptology, stuff like that related to how do you make sure that stuff is safe. So anyhow, diagnostic systems. I'm thinking them from the point of view of identifying the problem, like what Brett was mentioning about, quickly, and what's your reaction to that? Is it very rapid, or is it more of a long-term response? So those are the kind of things you can think about. Okay.
So in a moment, we'll make certain we have some time for each of you to ask questions of each other. I think we have a slide or two that Joe had for a quick illustration, if it's ready. There we go.
How do I just ask you to move or the slides or?
Yeah, that'd be fine.
All right. Number one, I wanted to thank Chuck and Infogard for inviting me and allowing me to speak. I'm a control system engineer. I'm also the managing director of the International Society of Automation's Control System and Automation Cybersecurity Standards. Those are the international cybersecurity standards for electric, water, oil, gas, chemicals, pipeline, transportation, you name it. Next slide, please. Okay, this is my little slide to explain why we're different and what needs to be done. When you're over here, this is what you just heard from the FBI and what they're looking at. That is Windows, that's Internet Protocol, it's what you're used to. Stuxnet affected what was called the programmable logic controllers. They don't look like IT, they don't look like anything else. What's actually inside those controllers, there really isn't any forensics for. It's part of the reason Stuxnet wasn't found, because they're changing logic. As you move further down, valves, motor control sensors, there is no security there. There is also effectively no cyber forensics there. This is in any industry worldwide. This is also why we need to train engineers, because they're the only ones who are going to understand what's going on at that time. That is not what the IT world is going to be able to see. This is also where you have catastrophic damage occurs. This is where you would have 2 or 3 day outages. That's where you have 9 to 18 month outages. Next slide, please, real quick. The other thing I wanted to point out, what we don't have, for anybody who saw Die Hard 4, there are no screens that say cyber attack. Unfortunately. This next one basically tells you this is real. I've been able to amass a database of over 750 actual control system cyber incidents, all industries worldwide. Almost none identified as cyber. This is both malicious and unintentional. We've already had more than 50 control system cyber incidents that have killed people. There's been over 1,000 deaths. There's been 5 major cyber-related electric outages in the United States already, none identified as cyber. So when you look at this, this is real. The other thing I wanted to point out real quick until I then show you one other real quick set of slides. People normally think of interdependencies between electric and everything else. There's another set of interdependencies that hasn't been considered. That's our vendors. What Stuxnet did was to exploit a vulnerability in the design of every single Siemens controller that was ever made. That means that same vulnerability crossed every single industry that used it. That's a totally different interdependency than has been addressed to date. Next slide real quick. One of the biggest issues we've got is sharing information and the policy associated to allow people to share information with a quote-unquote get-out-of-jail-free card. Right now, there's a disincentive to share any of this information. Next. Other direction? Okay. Last 3 slides, just so people know what they are. Aurora is a vulnerability that was demonstrated by the Idaho National Lab back in 2007. It's where they physically destroyed a generator. DHS, for reasons only they can answer, declassified 843 pages on Aurora. What I'm doing is showing 3 pages that are on hacker websites today. The first identifies by name the Pacific gas and electric substations you would use to destroy the rotating equipment in the Chevron Richmond refinery. Next. This is every large water pumping station in the state of California and how you would use the substations to destroy or damage the motors for every single large pumping station in California. Next. That's the natural gas compressor stations in the Northeast. This is where you would use the substations to destroy the natural gas critical infrastructure. So this is backwards. Everybody's wanting the grid to stay there. Here's where the grid can be a threat to industry. Last slide. Just the very last thing. Aurora occurs in less than 1 minute. It needs no other software. This is not a virus or a worm. This is effectively a mechanical, if you will, deficiency in the overall system that cyber can exploit. It is totally different. It's there. The hacker world knows it, and it's a direct threat to essentially all of not just American, North American, but any industrial infrastructure. Thank you.
Thank you, Joe. So we're going to hear more about space weather today, and we're also going to hear more about EMP. But all of you have a good background in each of them. For just maybe 30 seconds each from the end of the panel up, what are some of the hoped-for opportunities by addressing these systems? And I'm going to ask the question this way. Many organizations I see, including businesses, look at something like this and they throw their hands up and say, too complicated, I don't have time, I'm just going to hope for the best. Or it's too expensive, or I don't have the talent. Is there hope that if people do a really thorough systems review of all these interdependencies and get their hands around it, that they might actually save and make their companies money while avoiding a major disaster? Or is it so expensive to do that only a few companies can do it and the rest of us are just going to suffer as helpless victims to the complicated world we've inherited?
Yeah, that's a really interesting question, Chuck, and let me just say I'm not going to claim to be the expert in being able to answer all those elements in there, particularly the economic ones. But from what I have seen, though, is that the triage approach has been discussed a lot over the last couple of days, and it has also been written about, and with the idea that if you can protect a smaller number, say 20% of the grid, say in the transformers, large transformers, that you can result in the ability to protect 80% of the economic loss that would otherwise have occurred if you did nothing at all. Now, let me just say one of the things that I would hope that would come out of the INCOSE engagement in this. One of the things that I think would be beneficial in this is that being able to model complex systems, being able to look at the behaviors, being able to look at the interactions and identify the high leverage points. By the high leverage points, I'm looking for something that for the least amount of cost you can make the greatest amount of effort or the greatest amount of result. Those kinds of interactions are not always obvious, and it does take some good analysis to be able to pinpoint those. But once that work is done, I think it would save some work with respect to where we put our money and to provide an improvement.
Mark, anything to add? We have about less than a minute, so go ahead.
Okay. I've been involved in a lot of big programs, many systems, and the one thing I think I've learned over that, and I think it relates to the system of systems working group we have and others, is that in order to take on a very big problem, very big interrelated system of systems, and typically we will not address down to the detailed levels that like Joe's talking about. But if you break it down to where you start understanding the whole problem, and then start breaking up the individual pieces of working one area and another, you can work through that. And obviously interface, everything else is related to that, but you have to understand the whole problem in order to know where your priorities got to be, where the big issues are, and obviously when you focus on the three we're talking about, the solar, the EMP, as well as the cyber, you would then work on each one of those when you go from there. So it can be done. It's just a matter. It does take time, a lot of effort, and I think we probably all understand that part.
Thank you. Tom, you have the benefit of having gone first and last. In this case, the first shall be last because he's one and the same.
Well, certainly. I think this is an area where economic analysis can be very helpful. Let's look at opportunities where there are high-impact events that can be cost-effectively protected against. For example, solar storm impacts on the electric grid. We could protect all the electric grid for less than $1 billion, and then we could get a double benefit if it's done correctly. We also could get a nuclear deterrent against high-altitude EMP attacks. We wouldn't get 100% protection, but we'd get a deterrent. So we need to look at these opportunities which are very cost-effective, and as a society, decide strategically we're going to take care of these opportunities and then move on to other things which are more complex.
I think later today during our lunch break we'll hear some recently released data that's been done at Idaho National Labs and other places that reflect that there are day-to-day wear and tear experience of equipment such as the grid and consumers or commercial equipment that's dependent on it, that if they were taking a certain amount of protective measures against these issues, they would actually save wear and tear and actually save themselves money day to day while being better prepared for a larger event. And I think we'll hear more about that this afternoon. But I just want to thank the panel for being here today and thank all of you for spending your time with us today doing this. Thank you.